Hello again. Today we're going to be talking about how to find the volume of a solid by using cross sections. So let's get started. Let's say we have a function that has a closed area. We've done this before with integration, but now we're asked to find the volume of a solid where that area is the bottom side of that solid. So one way to do this is we take all those rectangles that we found before to find the area, and now we convert those rectangles to solids, all the same shape but with different sizes, and we create kind of a solid like you see there on the right. Now the size of that solid is going to depend on what f of x is as you move through the base area to create all of your shapes. Okay, so I calculate the volume one of three ways. There are other ways to do it, but we really need to know these three. Squares is one of them, and that will create a solid that looks like that. I could also create the solid by using equilateral triangles, and the third way is by using semicircles to create those three solids right there. So what I'm going to do is I'm going to figure out, okay, if f of x is the base of that shape, whether it's a square or an equilateral triangle or a semicircle, what is the overall area of that shape if I use f of x as the base length? All right, so I'm going to calculate the height of each of those shapes, and then based on the height and the base length, I'm going to be able to figure out the area of each of those shapes. So for a square, the height is going to be the same as the base, so that makes the area base times height, which is f of x times f of x, or f of x squared. If I have an equilateral triangle, then the height based on trigonometry is going to be y times root 3 over 2, and that's going to make my overall area 1/2 times that base of y times the height of y root 3 over 2. So the overall area, if I simplify that, is going to be root 3 over 4 times y squared, which I can also call root 3 over 4 times f of x squared. Now for a semicircle, the height of that semicircle is going to be exactly half of the base because the base is the diameter, and the height of that semicircle is going to be the radius, which is half. So the height of the semicircle is y over 2. That means the area is going to be 1/2 times pi times the radius squared, or 1/2 times pi times y over 2 squared. And that simplifies to be pi over 8 times y squared. All right, so when I add up an infinite number of squares or equilateral triangles or semicircles, I have to use an integral to do that. And so the volume for the squares is going to be the integral from a to b of f of x squareds. And then if I do equilateral triangles, it's going to be that same integral multiplied by root 3 over 4 based on the formula that we talked about. And for semicircles, it's going to be that same integral but with pi over 8 in front. So those are the three volume formulas you need to know. They all look very, very similar. It's just that there's a different constant out in front of the integral, depending on what shape you're using. So here's an example. Let's say I've got this region here. It is a semicircle. It's bound by f of x equals root 9 minus x squared, and it's also bound by the x-axis. So I'm going to form a solid with that semicircle as a base, and the cross sections are going to be perpendicular to the x-axis. Okay, that means that they are going to be going vertically. So I find the volume when the cross sections are each of those three shapes: squares, equilateral triangles, and semicircles. So if I'm doing squares, remember that's just the integral of f of x squared. So my a and b are going to be -3 and +3 because those are the x's where the region starts and stops. And my function is root 9 minus x squared, and I'm going to square that according to the formula, which gets me just the integral of 9 minus x squared, and that ends up being 36. All right, if I do equilateral triangles instead, then the question simply changes by putting a root 3 over 4 in front. I've already figured out what the integral is without the root 3 over 4, so I'm going to say that the answer is root 3 over 4 times 36, which is 9 root 3. And then with semicircles, remember the formula is very, very similar. Again, it's just that instead of root 3 over 4, it's got pi over 8 in front. Again, I've already figured out that integral of f of x squared, that was 36. So pi over 8 times that is going to be 9 pi over 2. Okay? And another example, a slightly weird shape this time, is going to be bound by f of x equals 2 sine x, and g of x equals the sine of 2x. Okay, so again, the same wording. A solid is formed by having that as its base, and the cross sections are perpendicular to the x-axis. So I'm going to find the volume when the cross sections are squares. So in order to figure out each of those functions, I'm going to have to subtract the two functions. 2 sine x is the function that's the upper function, and g of x is the lower function. So I'm going to plug those in as 2 sine x and sine 2x respectively, and it looks like the region starts at x equals 0 and ends at x equals pi, so those are the endpoints of my integral. If I figure this out, this is 5 pi over 2. So that's going to be the overall volume when I use squares. For equilateral triangles, it's the same value, but remember I've got a root 3 over 4 in front. So root 3 over 4 times 5 pi over 2 is going to give me 5 pi root 3 over 8. That's going to be the volume if I use equilateral triangles. And finally, for semicircles, I'm going to take that integral and multiply it by pi over 8. So I have pi over 8 times 5 pi over 2, and that gets me 5 pi squared over 16. So that's just a brief lesson of how to find volumes of solids by using cross sections. If you have any questions, please let me know, and I will see you tomorrow.